if you plot the dissociation rate for the motor as a function of f, generally you have this form, okay. But what we have observed that when motor is moving, then the force dissociation rate, if you look at the dissociation rate of the motor as a function of force, it increases exponentially up to the stall force, which is about 5 picon. Okay, so up to this point, motor is moving, and if you apply higher and higher force, its dissociation rate will increase. Okay, but once motor has stopped moving, which happens after the force of 5 picon, its dissociation rate start increasing linearly with the applied force, which means that it won't detach so fast as it was detaching before the stall force. And for dialing motor, okay, which moves from minus end to the plus end in the opposite direction, what we have seen that the dissociation rate will increase, okay, as you increase the force up to the stall force. Stall force is about 1.25 piconewton in vitro for dialing motors, okay, and after the stall force, it will start decaying with the time. So,
what do you mean by experimentally constant model means?
Oh, because these dissociation rates before stall and after stall have been obtained from the experimental data.
From experimental.
Yeah. Okay. So this is an exercise which you can do. Okay. So I told you about the force, linear force velocity curve. Okay. So you can assume that the rate of stepping, okay, is given by this expression where W is greater than 1. So let's say for W is equal to 2, because some of the kinesin motors are found to have this kind of force velocity curve, okay, and you can fit this force velocity curve with this formula 1 minus f upon fs to the power 2, okay. And then let's say my rate of detachment is given by an exponentially growing so my rate of detachment before the stall force when motor is moving, okay, is given by this expression, so that if you apply higher and higher force, motor will detach faster, okay. And when motor has stopped moving, so for forces greater than stall force, it increases linearly with the force, okay. The exercise is to calculate the average velocity for the value of the force 3 piconewton for 10, 100 and 1000 samples. And if you do this exercise, you will see that you will get very close to the actual velocity for large number of samples. And then you can also try to calculate the average time taken by motors to detach at f is equal to 6 piconewton, okay, when it is in the stalled condition. Again for 10, 100 and 1000 samples. Okay, so for dialing motor, we believe that there is something called catch bond. Okay, normally I mean the intuition is that if there is something, okay, if I try to pull it harder, it will detach faster. Okay, and for dialing, we think that there is a catch bond behavior. Okay, and the simplest model to understand is this: suppose you have two hooks like this. Okay, if I'm not pulling my both hands very tightly, then anyone can kick me and it will just break, okay. But if I start pulling very hard, okay, then it becomes very difficult to break it, okay, right, by hitting this kind of bond. So probably something like that happens for the dialing motor.
So one more.
Yeah.
So Monte Carlo is the only way by which we can calculate the motor motility property, or there is other method, or it is the best?
No, there are different ways of doing computer simulation. Okay, so Monte Carlo is a stochastic method. Okay, it's very good for a stochastic process where things are not deterministic. Okay, but there is something called molecular dynamics simulation. Okay, which is deterministic. Okay, and what is done that I mean in molecular dynamics simulation things are deterministic. So you are the state of the system using Newton's equation of motion. Okay. But this one is stochastic, so we use Monte Carlo. Do I have 5 more minutes or do I have to stop?
So just one question. Since you were starting with the assumption that it is a stochastic process, but you finish the calculation on this thing. But with this, can you still some way predict what will be the processability for each individual motor?
Say it again.
So this is stochastic because we don't understand when one motor is going to fall. So after all this calculation, will it be possible?
Yes. Because I mean, I can do this experiment for different number of samples, and for each sample, motor will detach at different times, right? Because it's a stochastic process. So I can plot the statistics of, let's say, detachment, okay, for different values of forces. So yes, you can get the histogram of, let's say, detachment time for single motor from the computer experiment. Yes, absolutely possible.
What I will do after this is kind of suddenly decided that I will do a half-an-hour talk on some simulations that we did, and probably I will try to emphasize on how we use experimentally available data to simulate a tug of war. Okay, it will nicely complement what Ambarish already laid out. So it can be a more interactive and but it's a completely unprepared talk, so everyone should be prepared for me to come to.
So what I wanted to do, I wanted to talk about some realistic model that we can do in the tutorial session.
So if you want to
take
a little more time.
Yeah, I think I will take 5 minutes. Is that okay? Okay, fine. So this is the exercise which you should try to do. I can give you the computer program, you can modify it. Okay, and try to do this exercise. If anything is not clear about the computer program which I gave you, do ask me. Okay, so people in experiments have also measured the velocity of the single kinesin motor as a function of ATP concentration. Okay, fine. Because these motors burn energy and then they stand. Okay, so people have tried to measure the velocity of the motor as a function of ATP concentration, and the velocity as a function of ATP concentration can be fitted with this kind of expression. Okay, is this called mechanism and kinetics, and one can fit the velocity as a function of ATP concentration as a function of force. So if you do it, if you plot velocity. If you have done the fitting and if you plot the velocity as a function of ATP concentration, then this is what you will get. That if you increase the ATP concentration, motor will move with the more velocity, and after some value of the ATP concentration, it will saturate. Okay, and if you try to plot the velocity as a function of load, because these rates like K catalytic, K off have the load dependence, so this is what you will get as a function of load. Okay. And this has been done for kinesin motors. So somebody has made a Monte Carlo model for this. This is a paper by Ruth Malik and Manoranjan Singh in PNS. So this is the reference of the paper where they have developed a simple model for kinesin motor. Okay, to understand this kind of dependence of velocity of single motor on ATP concentration and dependence of velocity on the load. Okay, so
why even after increasing the ATP concentration, velocity is constant after a point, because anyhow by providing ATP we gain energy.
Because it depends on the ability of, I mean, so it's like that. Okay, so you can consume certain amount of food. Okay, let's say 1 kg. Okay, in an hour. If I start giving you 10 kg in an hour, will you consume? You are constrained by something, right? Some factor. So it's the same thing for
So in the model also that is available when you generate a computer model. In that, when we talk about the cell, there are so many factors which could restrict the motion after a given point. But when you generate a computer model, in that there is no factors outside which are very low that could restrict your
Right.
So how do you make a comparison? How do you do that?
So, for example, I mean, I can use this kind of model to compare it with the in vitro experiments, because we can basically bypass all the complexities. Okay.
But at some point, you are underestimating the effect of ATP concentration in your computer generated model.
No, in this case, I mean, if I do the simulation with this prescription, it will give me the correct result. Okay. because this thing has been done. I mean, this is the data from in vitro experiment. It's not from in vivo experiment.
That is possible in vitro,
Hmm.
but when you do the in silico in that it is not possible that after a velocity is increased, at ADP concentration is increased, you will get the saturation curve.
No, you will see. You do that and you find that thing. That's why I'm recommending you this article. Okay, so don't read the paper. Okay, read the supplement of this paper. Okay, paper itself is nice, but with no office. Okay, so paper basically has a model for a single dialing motor. Okay, but that might be a bit complex for biologists. So what I'm recommending that you read the supporting text of this paper. You read the section on simple model for kinesin motor. Okay, what has been proposed. Okay, to understand this kind of dependence. Dependence on ATP concentration. Okay, and you read the Monte Carlo model of single motor. Okay, which you can use to make a computer model for this data. Okay, it's very nice work. So I highly recommend this. Okay, whenever I get confused, I go back to that article. Okay, so in this case, basically when we are doing modeling, we got all the structural details of a single motor, right? We just thought of that. Okay, motor is like a particle which can take a step and which detaches. Okay, we did not include the properties of the motor. Okay, but we know that motors have protein and they can be flexible. Okay, so as a next step, one can try to model the motors as a floppy linkage. Okay, so that when you try to stress the motor, it will exert a restoring force. Okay. And if you try to buckle it, it will buckle without any resistance. Okay, because this is how most of the protein molecules behave. Then what you can say that in my computer model that motors can step on the track and detach from the track. Okay, which will be determined from the stepping rate and detachment rates. And I already told you how you can determine the stepping rate and detachment rate from the experimental data. Okay. So in these kind of models, once motor moves, it gets stretched, okay, and then it applies a force on the bead. Okay, it will try to pull the bead, right, in the forward direction, and then you have to update the state of the bead at the next time step. Okay, so there are two ways to do it. If you don't want to include the effect of thermal noise, viscosity, everything, okay, you can just do a force balance, because you know that after the motor has stepped, okay, there will be a force imbalance. Okay, this spring will try to come back to its natural position and it will try to pull the bead. So you do a force balance and you basically move the bead until this spring comes back to its natural length, right? So that is one way of updating the state of the cargo. Okay, but if you have to include the effect of thermal noise and viscosity, okay, you can solve something called Langevin equation, and Professor Menon has already introduced this Langevin equation. So I'll just very briefly tell you what it is and how we can do it. I'm not going into. I don't want to get into a very complex situation, so I'll just try to explain you in a simple way. Okay. So Langevin equation. Langevin equation is, so all of you know Newton's equation of motion, right? What is that? Newton's equation of motion. Huh? No, that's not the Newton's equation. Okay. Have you seen this? Right? This is Newton's equation. Fine. Okay. Can I write this thing as mx double dot? Let's say, let's just do x by right? This is my Newton's equation of motion, right? So Langevin equation is an extension of, you can think of Langevin equation as an extension of Newton's equation, where there is a constant force term, okay, and then there is a stochastic force term, okay. Fine. So this F includes all possible forces on the motor. I can write this thing as, let's say, so let's say there is some external force. Okay. The other force which will be which will be the viscous drag. So I can write that thing as gamma dx by dt. Okay, right, and plus eta t. Right. So this is what is called Langevin equation. Right. So it's an extension of the Newton's equation, which has a stochastic force term. Now, Professor Menon has already told you that if you consider the cellular environment and the kind of environment a motor would feel inside, let's say inside the cell, if you compare this term, okay, and this term, this is my viscous term, right? This is my viscous force, gamma x dot, right? Which will try to reduce the motion of the bead, and this is my inertial term, which comes from the inertia, okay? And he has already talked about the Reynolds number, right? So Reynolds number is the ratio of inertial to viscous forces, which means that you take the inertial force and viscous force, okay? So the order of this thing is roughly 10 to the power minus 2. Okay, so it's called low Reynolds number situation. Fine. So we can ignore this term, completely ignore this term, and we can rewrite this whole equation as follows: gamma dx by dt is equal to, let's say, fxt plus eta t. Okay. And then this noise has to satisfy certain properties. Properties like if you take the average of this noise or force as a function of time, then average of this force has to be 0. Okay. And if you try to calculate a correlation of this noise at different time, okay, then eta t, and let's say at time eta t prime, okay, then this has to be 2 k bt gamma delta t. Okay, so this is called Gaussian white noise. You don't have to worry about it. Okay, so the thing is that when you are trying to do when you are trying to calculate the position of the bead as a in presence of thermal noise and viscosity, you have to solve the Langevin equation. And if you solve the Langevin equation, then what you so x, the position of the particle at time t plus delta t will be given by f times gamma. Okay, so this is called drift velocity. Okay, and you have to multiply this thing by delta t, and then you will have something called 2d delta t. Okay, so there is a prescription for calculating the position of the particle in presence of thermal noise and viscosity. If you take the simplest model, this is how you can calculate it. Okay, and I can give you the references. So we can use that thing and we can calculate the position of the particle as a function in presence of thermal noise and viscosity. So I will stop here.
In this case, we are completely considering that whatever the cargo is being moved by the motor is because of this the force that there is. So cargo is acting outside, motor is acting as a spring.
Right.
And all the force is applied by the spring when motor moves.
Right. Right. And that's possible, right? Because you know these motors have two heads. Right. So I mean, what happens when a motor is moving? One of the head will remain fixed to the track, okay, and the other one will try to move, right? And will try to move something like this, okay, and it will bind somewhere. Let's say, sorry, it will bind somewhere here, right? So, so stretching a motor is possible.
It is interesting to see how much physics can come in biology.
Well, biology is a difficult subject. Surprisingly, so far people didn't think of it as physics.
Okay, tea is ready. Very good. Tea is ready. Come for a quick tea.
So if anyone wants the computer program, I can share it.
Your earlier program you showed that type 0 to T and either stage or but is it possible that after detachment, the same motor can
Reattach. Yes.
Do you consider that?
No, for single motor it's out of question, okay? Because as soon as the motor is detaching, okay, we have calculated the run length and velocity, okay? Right?
But what happens to the motor?
The motor will go somewhere in the solution or in
The
inside.
vicinity and release thermal energy sufficient for
Right. So those events can happen.
you won't consider
For single motor model, we don't have to consider, okay? Because we just want to try to simulate a single motor, okay? But if you're trying to simulate a multiple motor system, okay? So let's say there are two motors moving, okay? One of them can be detached stochastically, and this one will be somewhere like this, okay? And it will be very close to the microtubule, okay? And this one can be divided. So for multiple motors, it's very important to consider.
Multiple motors to consider the competition of binding restriction.
Well, I mean, so let's say all the unattached motor will have certain probability to attach to the microtubule. Okay, so we look at.
So you minus the probability of the other binding.
So we have to consider all the possibilities for the binding. Okay, for each individual motor.
Start with the consider that motor is attached now with either motor.
So for single motor there are only two motors. I'm trying to do an experiment with a single motor. So I'm interested in this thing as well as it's moving. Okay. And once it has got detached from the back, I just want to complete things
Slowly, but it is important because if you are getting into this, the
Sorry, I took more time.
So reading a little bit, not much, slowly you have to read.
I mean, yeah, I think I cannot do so. The next one. My new PhD student, and electronics. Just this semester. Physics पढ़ाना पड़ेगा.
From here on. So she has formally joined.
Right.
Biological mind, yeah.
इसी में वो डिटेल बताते हैं क्योंकि मैं थर्मोलॉजी फर्स्ट ईयर कराना था बच्चे आ जाते हैं इसे मैंने कहा सबसे सिंपल चीज बताओ
They are required to work out the axonal so it can happen. Yeah, so my the result which I was talking about is particular.
Good. Yeah, I try to do a very simple thing.
Yeah.
this is a complex
Maybe it's I think people should and it's just to break the fear, and then people will study themselves. Where is Arijit?
So there is a mutant, okay, and it binds to Parkinson, which is working on the mitochondrial, on the which they have shown in the classification calcium binds to this. It undergoes a bifunctional change, means something like this. Okay. And once it does this, the Parkinson head, though it is bound to movement, that head binds to this. Or it gets distorted because Parkinson's bind to this movement, it gets attached to this portion. It binds to the base. Okay, and it gets destroyed somehow. Currently, it doesn't have movement. So that's what the happens. Right? That is it can take a flash or mitochondrial in the synapse, in the axonal synapse produces the but in the synapse, the main function is cell.
So, what I found from this paper, the importance is first is that this methane protein is required. Methane interacts with the neuroprotein, and this binds to the AG chain of cells. This is the key genes is called the feedback and
Same like
that's 2000. This one was the release of this is 2002 paper where we had first but I have just this is the fourth
this is like the delivery Parkinson molecule. This is the motor domain. Anything attaches to motor domain would not allow Parkinson to happen. So that's why the Parkinson has distinct domains. Motor domain binds to mitochondria. Tail domain binds to any carbon. Now plasmids can have attachments. Mitochondria has an attachment from which binds to in absence of liquor, it cannot bind Degeneration also. It requires no process. This is a protein. It doesn't have any process. Later on, they start forming the cytoskeleton and it makes this. And this is the growing end. Which later on forms cytoskeeleton. So, considering that, so the mitochondria are restricted to this one. They need to be transported to what they call as long exon late. So, it's easier way to travel mitochondria and then supply ATP to make ATP-rich regions rather than supplying ATP when it is required. Because sensing of requirement is not that fast. It's better if you send the mitochondria and they generally go to high ATP regions. So,
How do you sense it?
yeah, there are many complications where
Other than those
ANT,
cells and all that.
there are ANT,
How
ATP,
mitochondria
there
is
are
so
mitochondria. So, that is hypothetical.
even for sensing, you need the mitochondria there.
Yes.
So you can't sense them and send the mitochondria.
And so mitochondria, they have other things. They sensitivity ratio and they potassium as well. So there are a lot of things. So anyways, mitochondria are required in the axon for microtubule formation, blood cell transport, and anything which requires it.
Microtubule formation is
After that, so mitochondria are mainly on the major ATP production. And then they produce ATP as well as hormone in the hyperthyroid area processes.
So also another transformer synaptic process. This symbolic synaptic. Sorry.
Synaptic mitochondria is also present in the synapse.
In the gist that is on the synaptic mitochondria. So this is to really take a mental levels which will be negative. So it will be more transferable.
This is the
Yes. Yes.
So from there, we have nerves, which I think you will
Yesterday.
so they develop nerves. So I don't know whether they are so
Actually, we are using it, so you will tell me what is the problem it would be.
this is the word for
So what you can just keep doing what you're doing. You can't do too much now. Because the time was lost. You sleep and